time has come, the walrus said, to speak of other things, of why the sea is boiling hot and what's inside these bings. So hi, I'm Jim. As you may have guessed from the title, I'm going to tear into these Bing carburetors off of my Rotax 912. They're due. I think Rotax has had problems with floats sinking. These aren't supposed to be the floats, that were in the service bulletins, but I'm seeing some fuel staining and stuff, and plugs on one bank are a little black, so it's time. And since I have a background in carburation, I thought I'd take the time to kind of walk through how these carbs work, what the various pieces do, why somebody might do it that way, and as I tear it apart and see what I find. So there's going to be a lot of talking, so if that's not what you want, then sorry. But I should also say that I'm not an A&P. I don't have any Rotax specific training, certification, anything like that. I'm just a dumb old mechanical engineer who used to do a lot of emissions work in the auto industry back in the olden days when cars really had carburetors. So with that, let's zoom in and get started. Okay, real quick, in most carburetors you have a fixed venturi with a throttle plate down there and some kind of nozzle here, and as the air goes through this venturi or constriction, obviously the pressure drops as the air speeds up to get through there in accordance with Bernoulli's equation. That creates a vacuum or suction or depression, whatever word you want to use right here, and I'm going to use suction throughout this video. And that suction pulls fuel out of a reservoir over here, okay? And there's other variations, but that's probably the most typical carburetor design, okay? The problems are, it's pretty nonlinear. You don't get a one-to-one correlation between the mass of air flowing and the fuel coming here, so you play games like putting little air bleeds and jets in and mixing tubes and all kinds of fun stuff. And I've got more than a few hours playing with that stuff. To try and tailor, if you look at airflow mixture as a function, or air-fuel ratio as a function of flow, you try to get a curve, something like this, where this is a little rich at idle, it's a bit richer at high loads for power, a little leaner in the middle for economy, and there's just a lot of screwing around with jets and mixing tubes and things. But this Bing takes a different approach. It's a constant velocity carburetor, or constant depression, constant vacuum, different names. This right here, we're looking into the carburetor from the engine side, so the airflow is coming this way. This is the throttle plate, okay? So that would be idle, this would be wide open. And if we look at it from the other side, we see the, this is our venturi area here where the air comes through. And what this does, if I can get my finger in here, okay, as the airflow goes up and in the small restriction you have a lot of vacuum, as the airflow goes up, the venturi moves up and down automatically to maintain a constant vacuum, constant suction, constant depression, constant velocity through the venturi area, okay? So that would be where it would be near idle, and as you get closer to wide open throttle, it's going to pull up all the way there. So by maintaining a constant pressure, constant suction, I said I was going to use the word suction, in that area right here, okay, this place right here, this little brass thing, that's where the fuel gets sucked up out of the float bowl underneath. And if it was a constant suction all the time, you'd expect a constant fuel flow through that orifice there, right? But you can see this needle here has a taper, and as this moves up and down, the thickness of the needle going through that orifice changes, and by changing the taper in that needle, you can give it more fuel here when the slide is up, and reduce the amount of fuel at idle when the slide is further down, okay? So we'll tear into that and see what things look like in just a minute. I think I'm going to start with a float bowl. I'm going to weigh the floats and see if I suspect these floats have gotten heavy, but we'll see. Okay, so this is the float bowl. Normally it's sitting like this. This is fuel is held at a certain level in here. This is the fuel inlet right there. Yeah. So we'll cut the safety wire here. Come on, it can't be that hard. There. This should just, and there's probably fuel in the bottom still, but it's just a snaps, and I'll just pop it right out to get it out of my way. And there's the float bowl. No, there's no fuel in it. Okay. And these are the floats, okay? So as they go up and down, when this bowl fills up, they'll go up and down. And we can weigh those. Rotax wants to use a scale with a 1/10 of a gram resolution. This one only weighs to the nearest half a gram. I'm seeing 7 grams, so they're not horribly overweight. I think 7 grams is a limit, but they could be a tenth or two above. Not very clean for... But what those floats do, and this is upside down, is as the level rises, the level of fuel rises, okay? Let me do it right side up. As the level of fuel rises, it lifts this up, which presses on, oh, gasket's in good shape. Well, that could be part of the fuel staining problem, okay? There's a needle under here. I'll pull that out in a second. But as the fuel level rises, it presses on that, and that needle closes the fuel inlet here from getting into, to shut the fuel off, getting into the bowl. So it will maintain a constant level inside this bowl as, you know, and by having a constant level in here, you get a better control over the flow through this jet right here. This is the jet that goes up through that needle on the inside that we saw earlier. To get this out, there's a pin here, and if you probably can't see it, but that end has got some serrations on it. It goes in one way, it comes out one way. Ideally, you'd have a nice fine pin punch. Shouldn't take much to pop it loose and pull it out. There we go. And that, oops, comes out. There's a little retaining clip on here that holds, it's supposed to go through the hole in this. This is the valve that, when it's pushed up by the floats, shuts the fuel off. Doesn't look too bad to me. You know, you can see a little bit of wear, and on the other end there's this plunger, and there in the service instructions they talk about inspecting that to make sure it isn't worn and sticking out too much, but I'm going to replace it. Now, where'd that little clip go? There it is. It's little parts like this that get lost way too easy. Okay, I'll put that through there, put that on there so it doesn't get lost. I will replace all of that stuff. Okay, one more fun fact. To set the float level, excuse the shaking, I'm hand holding the camera. they want you to use this gauge here. The part number of the gauge is not on this page. It's near the front of the manual under the special tools. It's $80. It's just a piece of metal with a hole in it. And all it does is it measures down from the, essentially screw it into the casting in place of the main jet and measure. Yeah, I didn't order one. Maybe I would have if I'd thought of it, but I didn't. So, I've got the carburetor set up here. I got a digital height gauge, and the reason I'm hand holding it is I can't get it in close enough on anything convenient. And I've tried 2 different float arm brackets, okay? And I've tried both of the needles in here and one of the new needles, and there's variations, and what I can do is just slide this in. So I zero the height gauge up here. Okay, so that's off by 0.3 millimeters. I've been moving stuff around. Let me re-zero that. 0.03 millimeters. So I've been screwing around here. And if I bring this down, it's hard to tell exactly when it touches. You saw I went too far. Come on, focus, stupid thing. I decided not to focus. There, now it's focused. Explain that to me. So that's a 12.7. You can see it coming up. And there it's clear. And if I bring this one down, it's touching 11.5. 11.38. Somewhere right around 11.4 is where this particular, you can see it's touching there. As I slide this in, it just, as I slide this in, you can see it move, so it's touching, right? So that one is a little less than 11.38. And I've checked both sides. My best guess is, based on all the measurements I've taken, is 11.5 millimeters, 11.5 millimeters from this surface to here. And certainly if I check the new ones when I reassemble, yeah, thank you for focusing. When I reassemble, I'm going to be closer than as close as I am now, because that's 11.38 it's touching. If I slide the carb around, that is not touching, and I'm kind of assuming 11.52. I don't think that one's touching at 11.5, and I can check my zero in a second. 11.55. So anyhow, so that's my best guess at a number, and I'll also point out okay, so this is the other float arm, and you can see the worn spot. I was kind of feeling it with that's from my pen, those lines, but you can actually feel that dimple, and that's going to affect the number. That's going to affect the number because you got quite a bit of leverage. If you compare the distance from the pivot arm to that little dimple out to here, that's going to magnify that wear quite a bit. So anyhow, my thinking is if I check this and I'm in the vicinity of 11.5 millimeters down from right up here, and that comes back to 0. If I'm 11.5 millimeters down, I'm certainly not far off from where these carbs are operating today. Whether that's the correct setting or whether somebody's dingle-bopped around in here and bent something up, I can't tell you, but it's reasonably consistent, you know, with both sets of float brackets, both float needles, and I even stuck one of the new needles in there. So that's the best I've got to go on. If anybody has the dimensions for this tool, I'll try to put the number on screen. You know, particularly the distance between the bottom of the tool and I assume there's a flat surface inside here that sits on top of the main jet housing. It'd be a nice dimension to have. And if you've got the tool and wouldn't mind measuring and making a comment, that'd be pretty cool. I'd appreciate that. And even if it's too late for me, help somebody else. So rather than my number, which is shaky at best. So anyhow, moving on. That was tighter than I would have liked. Okay, I'm going to have to hold this better. I'll be back. Okay, so I clamped it in the vise like this with 2 blocks of wood so I didn't damage anything, and with the throttle partly closed. That, you know, I was careful. It's the thing with steel screws in this die-cast material. I like to either put anti-seize or Loctite. Doesn't matter which, but either one will prevent the corrosion. Oh, I got to take the spring off. Reduce the corrosion anyhow, and you got a better chance of getting things apart easily. Okay, slide that out. So this is the top, nothing much exciting there. Sorry. Just kind of. So there's a spring here. And this is the slide that goes up and down. There's a diaphragm here. And if we look, should be able to see, I can see the holes down the bottom. So the vacuum from that, in that venturi area, comes through those holes and is applied to the top of this diaphragm. And as the vacuum is too high, it tends to slide it up, right? It gets sucked up in there, and it becomes a balancing act between the vacuum on top, or suction on top, the force of the spring, and the weight of this whole assembly due to gravity, okay? Okay, this is what vents the underside of that diaphragm, by the way, and keeps it at the air inlet pressure on the bottom of that diaphragm. And this is that tapered needle that does the metering. You should be able to see the taper even on the screen. And the more you taper it, the faster the fuel changes as you lift this in and out. So getting that taper right determines how the fuel ratio changes with position. And there's also, well, I'll get it out in a second. There's this whole needle can move up and down in the assembly. Let me put. Now this does have a hole right here. I don't know if that's, there we go, now you can see it. That whole passage right there. I'm not sure what that's for. Have to think on that. So removing these screws should remove this metal ring, which will let me replace the diaphragm. Okay. that's the diaphragm. Little ridge here fits into that groove right there. Pretty groovy, eh? Now down inside here, can I get the light? You can see a screw head there. If I pull that, that's here on the exploded diagram. Okay, you can see that's that piece right there, and that retains the needle here. This is the needle. So of course you're operating more by feel than anything else. There we go. Okay. So I can set this back here. So there's the needle, and this holds it down. And this is there's a clip on the needle. I'm just looking, sorry. There's a clip and a little rubber, must be this 18, a little rubber ring and the clip. And this is in the 1, 2, clip is in the 4th notch up. So if I moved that clip down a notch, it would lift this needle up relative to the jet and just make it richer everywhere. But I'm not going to be messing with that part of it. So as we look down down from the top, let's try looking this way, if I can get it there. So we're looking up from the bottom, and you can see the light shining through this hole here. This is the main metering system. This is where that needle stuck into, okay? And that needle went into here, and as it went up and down, of course, that changed effectively the area of, okay, so you can see the this orifice here, or jet, is where the needle went into, and as that went up and down, that changed the effective area, or the annulus, between the needle and that jet to control the ratio of fuel and air, the mixture, okay? And that hole, if you get the light right here, you can see it goes all the way through, and this is the bottom of the carb, and it comes all the way down here through the main jet, and this is where you would suck the fuel up, okay? So that's the main metering system. And let me get some more tools and we'll pull the main jet. So if we look here, you know, this is where the fuel comes into the carburetor. That little orifice down in there is where that needle hit. This plunger hit that orifice down there that you can just see, or that little hole, to shut the fuel off when the float level gets high enough, or the fuel level gets high enough in the float bowl. So this is the main jet here, I believe, that controls the flow of fuel in conjunction with that needle. And it's just a little orifice there. Not a good idea to stick things like drills down those holes, okay? Put that right there. Okay, so that's the main jet screws into there, and that's just, I'm going to call it an adapter. Get that into there. And this just pops out, and that is the jet that the needle goes into. Okay, final part of the main metering system, main fuel system. You have this hole right here that goes straight back in and around this where that jet was, and in here, this was up inside there, okay? And you can see it has holes in the side. So this would have let air, so this lets air come in here and flow up into that area where the suction is and kind of mix with the fuel as it's bubbling out through the jet to make air fuel emulsion or bubbly or whatever. You know, there's the idea that you know, the fuel gets sprayed into the carburetor and atomizes in the carburetor. And if you've ever peered inside a carburetor as they're running, you find that the fuel is blobby, drippy, splattery, globs. Some of it evaporates. Most of it ends up as liquid on the throttle plates, and a lot of it ends up as liquid on the walls of the intake manifold. But, you know, getting some air and fuel mixing right as it's coming into the venturi area does help break it up and evaporate it faster. Okay? Okay, let's talk about the idle system. You know, we talked about the slide and the needle and going up and down and all that. Well, when the throttle is closed, okay, there's just not enough airflow for that system to work, so you need a separate system, the idle system, and let's walk through that. This is the idle jet. Let me lefty-loosey that. There we go. So fuel comes in the bottom of this jet. There's a little hole. And then comes out the top. And you'll notice there's a ring of holes around the outside. Again, right here, this orifice, okay, this orifice comes through and it goes along here and comes in to there to supply air. So there's air coming in the side, fuel coming in the bottom, and then you get this fuel-air mixture, they call it an emulsion, coming out the top of this jet. So the air bleed comes in this side, and the fuel goes down this side, and then this isn't drilled. This is just, you know, sometimes this stuff is just, wow, who thought of this, you know? And looking in here, let me... Okay, that hole right there is where the fuel comes out, that little small one, not this bigger one on the side. That little small one is the idle outlet, okay? And then under here, this screw, normally when I take this out, I turn it in first and count the turns, but I already had it out, and it was in about a turn and a half, a little over a turn and a half. And that's where it is now. So that's the idle mixture screw. You can see it's got that tapered tip, and it goes in an orifice, and as you screw it in, it constricts the flow. As you screw it out, it opens it up, so as you screw it out, you get more of the fuel or air-fuel emulsion into the carburetor, and you can adjust the mixture, okay? Nothing super duper, right? But there's one more thing. Oops. There's a spring underneath that underneath this to keep it from turning. Let's see if I can get you in here. Okay. Now down here in the bottom, you can see two little holes right there. See them? And one is getting covered up and the other is getting covered up, right? These are transfer ports, okay? These also go to that fuel passage and the fuel air passage. They just go right in the top. And when the throttle is closed, okay, you can see those holes are covered up. they're on the far side of the throttle, and they're going to be closer to inlet temperature than to the suction side on the engine side, suction on the engine side, right? Because that's how this idle circuit works. When the throttle's closed, the engine's trying to suck air out of the manifold, and you get a low pressure here, low manifold pressure, a lot of suction, and that's what sucks the fuel out of that, through that idle system, is that suction from the engine. But as you open this up and you start to uncover those screws, now they're, well, when they're this way, right, they're going to let air go into, they're behind the throttle plate, they're letting air into that idle system and reducing the amount of fuel by replacing some of it with air, right? So you get less fuel. And then as you open that up, now those holes appear on the suction side, on the low pressure side, on the engine side, and so they don't let air into there anymore. And now you get a more concentrated mix of fuel and air. You get more fuel. So as you open the throttle, the amount of fuel delivered increases instead of decreasing, because the vacuum's decreasing. So the amount of fuel slowly increases as that throttle moves and uncovers those ports. And as you get much further, you start to get the main jet active, and you get this smooth transition between the idle and part throttle, just because of those little holes where they're placed, and you know how big they are. And I gotta tell you, I don't know who originally came up with that idea. It's pretty typical to have transfer ports, transfer slots, but it's just mind-blowing to me, okay? To figure that out, to be able to make this system with just, you know, orifices and passages and bleeds and make all this work, that you got that smooth transition from the air fuel you want at idle to operating at part throttle with, you know, fuel coming from a totally different system. It's genius. I mean, whoever came up with that idea was a flat-out genius. And you know, the average person looking at this carburetor, even if you handed it to them like this, would they even notice the holes? Would they appreciate the kind of inspiration that went into coming up with a setup like that? It's just amazing to me. So anyhow, that's idle. Let's move on. But anyhow, so we'll be adjusting this to get the mixture right at idle when we get it back in the airplane. Back in the olden days when I did this sort of thing for a living, as an engineer, you had to wear a tie all the time, you know, so you're adjusting idles, working on a car under the hood with the engine running, wearing a tie. I mean, how stupid is that, you know? But that's the way it was. And there's the spring that went with that. The spring just keeps it from turning by itself, okay? The throttle. Now the throttle, there is an O-ring in here, but these screws they're staked. You can see where they're squished. I'm not going to pull those out, right? There's just too much chance of screwing something up with very little potential benefit just to replace that one O-ring, and I don't think I'm having issues with leakage around this, so I'm leaving that alone. I'm just looking at this. This is the vent for the float bowl and stuff. Looks like the passage is drilled all the way down here. If I were to guess, I would say that those two holes there are the vents to this thing for the overflow. Yeah, so probably this is drilled in like this, and then this hole here is drilled in up there to meet. Okay, that would make sense. So this is actually a bypass carburetor, not a choke per se. You know, a choke would be something like the throttle valve that closes off, except on this end of the carburetor, on the air intake side, the air cleaner side, so you choke it off the airflow, so you create suction inside the entire carburetor and you pull more fuel in. Now I'll talk about the fuel starting carburetor. Okay, so the starting carburetor, or choke, it's not really a choke, lets air in here, comes out here. This little hole here is connected to that. That's the fuel getting sucked in there. And then this hole here comes over to here behind the throttle plate. And you can see with the throttle plate closed, this is the engine side. As the engine sucks, it's going to suck through. It's going to suck pretty hard on that, which sucks here, which sucks up the fuel, which sucks up the air. And then this normally sits so this sits here. You know, this is the housing on top of it. You're used to seeing that. This hole here lines up with that when the choke is on, okay, or when you're enabling the extra fuel. And then there's holes down here that line up with this, and a little passage behind this brass disc, which you can't see, and I'm not going to take this apart because I don't need to. So as you rotate this, you know, you have the enrichment turned off. Then when you rotate it here, you open that passage up and open this up to the fuel on the bottom, and that enriches your mixture for starting, okay? But again, you have to have the throttle closed to get the suction through there to make that whole thing work, okay? Okay, now that it's apart, one thing I forgot to mention, sometimes I read, you know, like in discussion groups online, that this carburetor automatically compensates for altitude. No. Yes, it's a constant velocity. I think Bing likes constant depression. You know, constant vacuum, whatever term you want to use. But it's still the same concept in that you have the venturi creating the suction and the fuel coming through the metering jets, and the density of the air changes with altitude. The density of the fuel doesn't. It doesn't compensate for altitude. So I certainly don't find anything in any of the Rotax documentation, and I'm sure you won't either. But if you do, point me towards it, because prove me wrong. What the heck? Okay, so next up, I think I'll wrap up this video here. Next video, we'll put it back together. And I hope you found this useful, and catch you on the flip side.